Hello, my name is Brian Brown. You are joining the Open Hardware Platform for the Carrier Crowd webinar, and we're very, very pleased to have you joining, and thank you for attending. I will be doing introductions up front. We have three distinguished speakers. I myself, as Brian Brown, will be acting as the moderator. So my personal background is that I am VP of Advanced Solutions Development for Artisan Embedded Technologies, 20-plus years experience in the networking field with Alcatel-Lucent. Doug Sandy is CTO of Artisan Embedded Technologies and leads the groundbreaking strategic initiative programs that we are working on related to developing solutions to meet the emerging trends in Web 3.0, cloud computing, NFV, SDN, and accelerated video content delivery. Doug was previously CTO of the Emerson Embedded Computing Group, which was the name of the organization prior to us becoming Artisan Embedded Technologies. And Doug is also CTO of the PICNIC Group, the standards group related to ATCA standards development. Martin Taylor will also be joining us. Martin Taylor is the Chief Technical Officer at Metaswitch. Martin has spent over 20 years in telecom and the network equipment industries. At Metaswitch, and specifically, he has led product development strategies in hosted business services, web services, APIs, UIs, software-based SBCs, as well as unified messaging, plus responsibility for the evolution of product line development for both IMS and pre-IMS networks. Last speaker is Martin Horn. He is Senior Systems Architect with Broadcom. Martin has been a pioneer in the Broadcom's Processors and Wireless Infrastructure Group, and he is a veteran of the networking industry with over 20 years of technical experience with processors and networking. So that is the introductions. The full introductions and bios are available on the landing page for this webinar. For all the attendees out there, please feel free to ask questions using the question button and section of the webinar screen. Please feel free to ask questions throughout the course of the presentation. We will, however, be presenting continuously, and we will be addressing the questions at the end of the webinar. So with that, I would like to turn it over to Doug Sandy to start the presentation.
Thank you, Brian. It's a pleasure to be here this morning. The information that Artisan is going to share with you today is based on a recent survey enabling the carrier cloud, the evolution of software-defined networking, and network functions virtualization infrastructure. This survey is, the final report is being wrapped up, and we will make that available to participants in this webinar. What I'm going to do in my presentation is I'm going to cover some high-level market dynamics within the communication service provider space, look at some of the motivations behind software-defined networking, or SDN, and network functions virtualization, that's NFV. We're going to look at requirements then for SDN and NFV infrastructure hardware and the current activities around NFV infrastructure definition. Okay, let's take a moment and I'll let you digest the information on these charts here. The left chart is based on the Cisco Virtual Networking Index, and it shows the projected network capacity growth through 2018. Video is the predominant driver of this trend, and you can see it's a very, very large upward slope in capacity growth. Mobile carriers will feel the bulk of this with about 61% CAGR, compound annual growth rate, through that time period, although the fixed internet providers will also see a 20% CAGR over the same period, which is still a significant amount of increase. That alone isn't a problem, but the right chart is exemplary of another trend that's going on in the industry. The right chart there is based on China Mobile. It shows the ability of the CSPs to actually monetize the growth. You can see there's a big mismatch here. China Mobile is looking at driving toward 300 times capacity increase with only a 3 times increase in average revenue per user. And if this was just China Mobile, that would be one thing, but this is really an industry trend that's going on. So you can see from these two sets of numbers that CSPs are in a bind. They need to be able to scale capacity while containing their capital expenditures, and at the same time create new services and applications in order to raise top-line revenues. Software-defined networking and network functions virtualization are the newest tools in the carrier's toolbox, and they're really hoping to use these software technologies to help with the revenue and services issues that we saw in the previous slide. SDN separates the control plane of the network from the data plane in order to enable better configuration, management, and network efficiencies. Network functions virtualization, or NFV, on the other hand, virtualizes the underlying network function hardware, enabling rapid service deployment with a focus on running on enterprise-grade white box servers. Solutions for these are still under development, but the clear hope is that these two software technologies would transform the capabilities and the economics of the next generation network. I like this quote here from John Donovan of AT&T. It really shows the commitment of the CSPs for this migration, toe tagging existing assets with a rapid pivot to the new environment. Given the price-performance squeeze that the communication service providers are under, this slide is really interesting. Frankly, at Artisan, we were quite surprised by the survey findings in this regard. See, although the CSPs are committed to network functions virtualization and software-defined networking, the amount of enterprise COTS hardware that AT&T and Verizon expect to be deploying as late as 2017 is only in the region of 10 to 12% of their overall spend. This is in a really stark contrast to the need for the rapid pivot to the new solutions and economic models. I should say here also that although we show AT&T and Verizon here, we did get inputs from other communication service providers as well, and AT&T and Verizon represent the most aggressive cases for deployment of enterprise COTS. Part of the slow rollout of enterprise COTS is undoubtedly due to the maturity of SDN and network function virtualization software solutions. However, enterprise COTS hardware itself also poses challenges in terms of scalability and efficiency, especially in applications where very high capacity or lowest latency constraints are required. So while most of the focus today is on SDN and NFV software issues, there is a growing understanding that COTS infrastructure must also evolve as significant deployments of SDN and NFV are to become a reality. What's needed to accelerate the adoption of SDN and NFV solutions within the network is communication service provider COTS, or CSP COTS solutions. CSP COTS is a true off-the-shelf, open, multi-vendor ecosystem that addresses the specific needs of the CSPs. Since these solutions better fit the needs of the CSPs, they can accelerate the rate of adoption of COTS hardware within the network and enabling a more rapid pivot to SDN and NFV. Although the creation of an ecosystem may sound difficult, all it really takes is agreement between multiple vendors and multiple customers around the products and solutions that will be produced. Standards organizations often play a central role in this agreement. Advanced TCA from PICMIG is a good example of how customer and supplier engagement created a new ecosystem to serve the specific needs of the telecommunications equipment providers. ATCA was developed in 2001 in order to meet the express needs of the telecommunications equipment manufacturers, or TEMs, specifically around modularity, reliability, and service availability. Today, the ecosystem represents hundreds of suppliers with tens of thousands of systems deployed in every major network worldwide. Now, I'm going to digress from this chart for just a moment. If you're a CSP, you may or may not have heard about Advanced TCA, or ATCA for short. Chances are, though, you have it in your network. If you have heard of ATCA, you might not think of it as an open platform, though, because you're probably purchasing it today as part of a specific network appliance from an equipment manufacturer. There is, however, nothing that prohibits you from purchasing advanced TCA equipment directly from the suppliers today and then benefiting from the benefits of CSP COTS ecosystem. The next slide that I want to show has attributes for CSP COTS infrastructure solutions. And before I show it, I'm not going to do a formal survey here, but I just want you to think about what are the attributes that you would want to see in a successful CSP COTS ecosystem and successful CSP COTS solutions. In what areas is enterprise COTS good enough? What attributes need to be different for CSPs? So although we don't have the ability to run a formal survey right now, I would like to hear from you, and feel free to send me an email with your thoughts if you'd like. Okay, these are the high-level requirements that Artisan has come to understand when engaging with CSPs regarding CSP COTS. Scalable, secure, flexible, open, stable, high performance, and available on time. Are the attributes you expected in this list, or are there some missing? I'd like to underscore a few. Scalable and high performance. Now this means different things to different people, but we know in the context of the CSPs, network elements can benefit from higher capacity per node than traditional enterprise functions. They may also benefit from specialized processors and hardware acceleration beyond what traditional servers have. Now, as long as the virtualization hides these differences between traditional servers and the CSP COTS servers, then the NFV model doesn't get broken. Another thing that's a little bit different between enterprise COTS and CSP COTS is that the stability of the ecosystem needs to be much more stable. For instance, some enterprise-centric organizations in the industry are generating a lot of new innovation right now, but the technology churn rate is really high. While this might be acceptable for the enterprise deployments and enterprise companies, CSPs tend to prefer much less churn. Our challenge for CSP COTS is to embrace the technology innovation while still providing the stability that the CSPs require. The bottom line here, though, is that CSPs are focusing on software issues right now. They're looking to equipment manufacturers to help them address their platform needs. Artisan has always played the role of ecosystem steward in the industries in which we play. We were instrumental in the development of ATCA, and we're the leading supplier of standards-based COTS equipment in telecommunications. Today, we have a three-pronged approach in order to meet the CSP COTS needs of our customers. First, we have ATCA now to meet CSP COTS needs today. Advanced TCA, as we saw, has a broad, stable ecosystem and is a proven telecommunications technology. We also have PCI Express accelerator cards that can improve the performance of existing deployed enterprise solutions. By inserting a PCI Express accelerator card for something like video transcoding, you can realize the benefits of specialized acceleration hardware at a fraction of the cost of deployment of new enterprise COTS solutions. Third, we're actively engaged with CSPs to define the next generation CSP COTS requirements and drive them into standardization. I want to just mention the picture to the right there. That's an image of a next generation CSP COTS demo platform that's based on Open Compute, but it incorporates the requirements unique to CSPs. We don't have time to go into all the details of this platform today, but if you're interested, please contact us and we'd be happy to go into more detail and even possibly schedule a visit to our lab. Artisan is moving forward to make next generation CSP COTS a reality, and we want to hear from you in order to make sure that your needs are met. Now I'm going to hand over the presentation to Martin Taylor from Metaswitch.
Thank you, Doug. So I'm participating in this discussion representing a pure software vendor. So I'm going to try and give a software vendor's point of view around this whole question of CSP COTS as an enabler for the transition to SDN and NFV. First, a word or two of introduction about Metaswitch Networks. Metaswitch Networks has a long history of providing communication software. We've been around for more than 30 years. And over the last 15 years, we've been supplying voice networking solutions to telcos. In the last couple of years, we've also been quite widely recognized as a pioneer in the area of network functions virtualization, both because of the technology deliveries that we've made to market, for example, virtualized SBC and virtualized IMS designed from the ground up for the cloud, but also because of the customer engagements that have been announced, including the AT&T Domain 2.0, where we were announced as one of the first 4 vendors back in February this year, as well as very early deployments of virtualized SBCs, for example, in the British Telecom network in August this year. As a pioneer in the NFV space, the thing that we're most interested in and concerned about is the extent to which the hardware infrastructure underlying NFV and SDN is capable of supporting our virtualized network function software products effectively so that they can be deployed in the market and provide at least as good service as equivalent hardware-based products. Now, with all the excitement around SDN and NFV, it's easy to lose sight of the fact that products today, telco products being shipped into the market, primarily based on some kind of proprietary or semi-standard hardware platform. Now, I'm sure Artisan would characterize ATCA as very much a standards-based architecture, and certainly our approach has always been to integrate or combine our software with commercial off-the-shelf hardware, and right now that means ATCA. So today we ship all of our products with the exception of our virtualized IMS core, which is pure software. All the other products we ship pre-integrated on ATCA blades. The vast majority of these products are running on x86 server blades in an ATCA form factor. So they're essentially portable software products, but they're deployed on ATCA blades. We have a media gateway product also which fits into the same system, but clearly that requires specialized hardware for the media gateway function. And ATCA brings a lot of value to our customers. It's widely regarded as a reliable and manageable platform. There's a great deal of familiarity and comfort around this kind of hardware, which has been specifically designed for telco deployments. Of course, in some markets, particularly North America, NEBS compliance means that the hardware has passed some stringent tests, including resistance to earthquakes and fire and so on. And those kinds of attributes are regarded as very important by many of our customers. We've been a long-standing customer and partner of Artisan. They supply all of the ATCA hardware that goes into our products right now, and that partnership continues into the era of NFV in a sense that, for example, we have demonstrated together a proof of concept of an elastic SBC running virtualized on ATCA hardware. We are moving ahead very quickly to make all our products available as virtualized network functions. And in fact, they're all available today for trials and will be fully generally available by the end of this calendar year. Because the software was essentially designed to be portable from the outset, we've had very little work to do to get them running in a virtualized environment. We've had to make a few adaptations around software license management and APIs to assist orchestration. But essentially, it's the same code as you would be running on an ATCA platform on bare metal. Now, one of the key things that has to happen as one moves products from bare metal to an NFV environment is understanding how they perform and how they behave in that kind of environment. Our experience has been generally that products that operate purely in the control plane continue to work very nicely in a virtualized NFV environment, but products that place a lot of stress on the user plane, user data traffic, media traffic, and so on, are somewhat more demanding on the underlying capabilities of the platform. And I think that's for us is probably the most important aspect of the underlying capabilities of the hardware that is supporting the NFV environment. So, as I said, our key concern here is, in terms of the hardware environment, is how effectively does it support the virtualized network function software products that we need to deploy on it. And remember that we're not supplying the underlying platform. The telcos are generally putting that environment in place, the hardware, the hypervisor, the cloud operating system, and we are then providing the virtualized network function software packages that they deploy on it. Clearly, there's an important interplay here between that software and the underlying infrastructure. And as I said, what we've determined so far in the testing we've done is that control plane products like the IMS core, telephony application service, media gateway controllers, those kinds of things, they're compute intensive, not particularly I/O intensive. And from the point of view of the infrastructure, they look a lot like standard information technology workloads. And so generally we found not too many performance issues when running on general purpose compute platforms. But the user plane is much more challenging. And in the case of our product line, it's the session border controller that exercises the user plane with media traffic. So we're talking about relaying large numbers of media streams, performing encryption and decryption on those media streams, and performing audio transcoding. So the user plane challenges that we see in connection with the session border controller firstly concerns our ability to handle large numbers of small packets. And this is something that enterprise COTS hardware is generally not concerned with. Dealing with millions of minimum size packets per second as opposed to dealing with large bandwidth kind of web access or file transfer access or those kinds of workloads, it places a very different kind of stress on the hardware. Secondly, those media streams may well be and increasingly are encrypted, and that often means that we're having to do some kind of interworking between secure RTP and unencrypted RTP. And that encryption and decryption is very compute intensive and can soak up a large amount of hardware resource. And so the cost effectiveness of a virtualized SBC that's doing a lot of this encryption may depend on the underlying performance of the hardware in this encryption-decryption role. And then, and probably the most concerning of all to us right now is the question of audio transcoding. Video transcoding actually is generally reasonably well catered for on x86, but audio transcoding right now is relatively inefficient operation on x86 hardware. DSPs, which are purpose-designed for audio transcoding, are just much more efficient in terms of power and density. So again, the concern is that a virtualized session border controller that's doing a lot of transcoding in the absence of some kind of DSP or hardware acceleration solution may be considerably less efficient or cost-effective than a piece of proprietary hardware, and that's clearly not going to be acceptable as people move from proprietary hardware to an NFV environment. So there's clearly a role here for hardware assistance or hardware acceleration for these kinds of functions that virtualized network appliances are going to need. So if I can sum up our view of this whole question of COTS for communication service providers, I'd start with the observation that CSPs do have a level of comfort and familiarity with ATCA. The vast majority of telcos will have a very substantial population of ATCA appliances in their networks, and will be very comfortable with the idea of hardware that has been specifically designed for telcos. And I guess the converse of this is to say that while telcos may use a lot of enterprise COTS hardware in their IT operations, there's certainly a lot of concern about whether that hardware is appropriate for the network services that they deliver in supporting SDN and virtualized network functions. Technologies like ATCA are particularly interesting in the transition from hardware-based appliances to NFV, in that they are capable potentially of supporting heterogeneous environments. So the idea that you could have proprietary hardware blades alongside Intel architecture blades supporting virtualized environments in the same chassis, that's certainly an interesting concept, interesting possibility, and maybe solve some problems as we transition from the old world to the new. I mentioned the role of hardware acceleration. Clearly there are many other examples of functions that could benefit from hardware acceleration. I mentioned audio transcoding, I mentioned encryption and decryption, but clearly other kinds of network functions involving deep packet inspection, for example, may well benefit from hardware acceleration. And those kinds of functions really have no place in enterprise COTS hardware, and clearly CSP COTS could incorporate those to meet the needs of this particular market. We know a lot of CSPs are now engaged in trials of NFV. Many of them are doing that on enterprise COTS hardware. We can certainly expect some of them to start identifying some of those shortcomings. But our view certainly is that there is an opportunity for COTS hardware that's been specifically designed for this kind of environment, and that hardware may well look significantly different from enterprise COTS. I'm going to hand over now to Martin Horn, our next speaker.
Hi, I'm Martin Horn from Broadcom, and I want to talk a bit more about this trend that the other speakers have been mentioning, particularly network performance and how that factors into empowering and enabling NFV going forward. Broadcom is a silicon provider, and we're already pretty well established in the data center and networking space with PHYs, MACs, switches, and fabrics, and also multi-core SoCs. And today I want to focus primarily on the multi-core SoCs. So Broadcom has traditionally made multi-core processors that are applicable to the SDN, NFV, and control plane spaces, but primarily for end equipment vendors. And with the evolution of NFV and the separation of software and hardware, and the migration to a more common compute model, that family has been progressing. So the current multi-core processor family from Broadcom is the XLP 9XX family, the 980 being the higher end part. So it has 20 cores on it for a total of 80 hardware threads. And it's designed to handle networking throughput of about 160 gigabits per second full duplex. And that's on small packets. And it's a virtualized MIPS architecture. So moving forward, we have produced one more variant of the XLP family, and that is the XLP 500. And that has 8 cores, and that's designed primarily at the control plane and power-conscious markets. But to focus on NFV, one of the prime things that we've learned is that for applications to be portable, they actually need to be portable to similar compute capable platforms. So the single-threaded performance is crucial. So moving an application from an i5 family or i7 family processor down to an Atom, the applications would have to be refactored, and that's not very easy to do. So what we've done is we've developed a new class of multi-core SoC, and the family name is Vulkan, and it is a superscalar ARMv8 processor, and it has similar performance to the existing compute platforms. And it has up to 32 cores, which are four-way threaded, so 128 CPUs on board. And it's based on current technology, 16-nanometer FinFET technology. So with the Vulkan product line, like I said, it is ARMv8, so it is a standard ARM processor. However, Broadcom is a full licensee of the ARM technology, and so we're able to develop a custom V8 core, and it is truly a superscalar multi-issue processor. And we've designed it to have, for the same frequency on a per thread basis, roughly the same performance as a Haswell class processor. And this is to make the software transition very smooth. The other thing that we did is we've put more CPUs on the same socket in order to improve the scaling and to avoid the sort of issues you have with the NUMA technology and with peripheral affinity and latency. One of the key problems in NFV going forward is the problem of network virtualization, and particularly bandwidth for the network to the application, the guest applications. On the left-hand side, we show the existing architecture, and we're showing using DPK or PCIe virtualization model. And you can see that initially data has to go through the physical interface of the PCIe, and it has to be copied into the root kernel or hypervisor's memory space, and that's where the vSwitch or soft switch has to classify and decide where the payload needs to go. And it then gets copied up into the guest or VMs. And this consumes quite a lot of the CPU, and it involves quite a bit of latency, and this is one of the things that limits the throughput for particularly data plane applications. The ideal is to just have the packets go directly into the user memory space and have no real overhead for the packet. So the performance for virtualized functions are exactly the same as bare metal functions or applications that owned the physical interfaces. So that's what we've done with Vulkan. We've put in some coprocessors and some and acceleration, essentially in the SoC, that allows us to pre-classify and DMA the packets directly into L3 and into the memory space of the guest. And this eliminates all that overhead that exists today. Another subject that's been mentioned a couple of times also is the infrastructure. Now, ideally, we want to have an infrastructure that's independent of the different hardware platforms, the instruction sets, and that's very doable today. And we support an organization called Linaro. This is a multi-vendor organization sponsored originally by ARM, and ARM has been working, or Linaro has been working on solving the guest or data plane application API standardization. Within Linaro, there are a number of working groups. There are working groups that have been doing a lot of standards work on the load process, on virtualization, and even video. But one of the work groups is the networking work group, and within the networking work group, they've sponsored a set of APIs called the Open Data Plane. And this is truly an open API, an open standard. It's designed to abstract not just networking peripherals, but also crypto and other hardware accelerators as well. And it's designed to do that at a fairly high abstraction layer to make it very portable. And it also supports a user space scheduling model called Event Manager. And this allows people to develop applications, particularly data plane applications, that are very scalable, can be dynamically loaded across the CPU so that they're not tied to any specific CPU count or affinities, and also have a very simple programming model, the run-to-completion design pattern. The Open Data Plane organization is supported by multiple hardware vendors, and so it will ensure that the standard evolves and can be more widely used by developers. And these vendors are not just hardware vendors. So we have a few silicon vendors, but there are also software or ISVs involved, and also some systems vendors as well. So this is a very busy diagram, but we wanted to be able to, in one slide, just walk through some of the evolution that is occurring in the network virtualization problem space. So I have sort of 3 bars here, and they're color-coded, and I'll sort of explain them as we go through. The idea here is just to show some trends that have been occurring, and there are people who are at different phases of this, and hopefully you can relate to where you are and some of the trends that other people have recognized and solved. Initially, for virtualization in standard Linux, we use bridging, and it consumed as much as 50% of the CPU to actually implement that network virtualization. And so, from a throughput perspective, we have a certain level, and we have the system power. And it didn't really require any special network devices. The next evolution was OVS or virtual switching, and they were able to reduce the amount of CPU overhead and increase the networking throughput somewhat. But the system power and cost didn't really change. However, the performance wasn't that great, and so with PCIe virtualization, SROV, they were able to move the virtual switch into the root kernel's user space, and again, reduce the amount of CPU overhead, and again, increase the networking throughput. But these newer networking devices consumed a lot more power, and so the actual power and system cost went up somewhat. The next thing that we've seen occur out there is this concept of offload or virtualization offload. And here they've used names like SmartNICs and that. And so there, the CPU utilization goes down considerably because often it's completely bypassed. The amount of performance varies depending on the solution, but it generally is increased considerably. And these SmartNICs do consume quite a bit more power. Now, a lot of the CSPs considered this as sort of a non-standard approach, and so they have gone out and either privately or publicly developed more optimized vSwitches, and so they've managed to get the CPU utilization down to around 10-15%, and get slightly improved network performance over conventional, say, OVS. And they would still require, though, the PCIe virtualized NICs. So the power budget is comparable to the third model. there's another model out there, which I know Martin also suggested, and that is what's been widely called disaggregation. So this is where you use an acceleration platform in the data plane that has more specialized services, and it's more optimal in power and throughput. And there, what happens is the actual control plane is separated, and I have another diagram coming up about this model. And so the effective amount of control plane CPU is reduced considerably. The overall power budget is reduced, and the amount of networking throughput is increased considerably. And then in the Vulkan model, what we've done effectively is we've reduced the amount of CPU overhead for network virtualization, and we're supplying up to 200 million packets per second full duplex of throughput. So we've really increased the I/O model, and we're also reducing the power because of our CPU density. So disaggregation doesn't break the NFV model. So what a lot of carriers have determined is that the compute platforms have some limitations, and the network platforms have some limitations as well. So if they use a third platform, and they call it either a network accelerator or coprocessor, they split the control plane and the forwarding element and the service function chaining elements. They can actually conform to NFV, but deploy immediately. And so this is an approach that a number of carriers are using. And more recently, we worked on an NFV POC number 21, showing this specifically for IPsec, because our processors also include crypto coprocessing. And we showed that at a minimum, the speed up for this model over a conventional IA server-based model is more than 10 to 1, and it depends on the platform. But that's what you can go to that POC and have a look at the test results. The ecosystem for ARM is very, very strong, and it's driven largely through Linaro. So it includes for managed applications like Java and compressed PHP. Those types of environments are also already established. It supports a lot of different hardware vendors, and the objective for Linaro is that the actual Linux binaries actually be compatible on all vendors. And the one thing about the ARM instruction set, it is actually constant across all vendors. It cannot be modified. So it's a very, very strong ecosystem. They've also developed a base set of abstractions for server class platform to make it very, very easy to port operating systems from platform to platform. So there's a minimum amount of work that's really required, and some vendors have shown that it can be done in less than a couple of days. Broadcom works with a wide range of ecosystem partners. So for development, so contract development, for operating systems, for pre-built applications, like classification, and networking services, involve packet core, and we'll continue to do that. So in summary, Broadcom is looking at empowering the NFV environment by building best-in-class ARM V8 core. So that means that we can provide comparable performance. We have industry-leading packet processing performance, and we're providing the necessary hardware acceleration to enable not just software virtualization, but also software service chaining, and it's adaptable enough to accommodate any even proprietary protocols or new developments in the future. We have provided internally in the architecture virtualization not just for the CPUs but for all the peripherals, so that when virtualization is used, that they can all be all the applications can cleanly and effectively share the co-processors. And lastly, but not least, is that with our solutions being SoCs, and actually with the amount of CPU power that we're putting in a single socket, we can also help with power management and scaling per watt. Thank you.
This is Brian Brown, the moderator. I would like to thank our three speakers for their very informative presentations. We now have some time for Q&A with Doug Sandy, Martin Horn, and Martin Taylor. To submit a question, please just type into the comments box on this page, and the answers from the speakers will appear as text in the comments stream. Thank you very much for joining our webinar. Please feel free to reach out to the speakers directly with questions. Their email addresses will be contained in the back of this presentation, as well as the landing page for this webinar. There is no audio element associated with the Q&A, so this will conclude the audio session of this webinar. Thank you again.